So I really don't know any other way to describe that except this. So that's what we'll go with. All right, so here we go. The idea is that, and it's not straightforward, but if you have any two conductors in space, no matter what, any two conductors in space, and you apply a conducting pathway between them that includes a potential difference, you should be able to drive charges from one to the other. The potential difference is going to move the charges from one side to the other. So based on the way I've drawn this, making this side positive and this side negative, an equal amount of positive charge will appear here and an equal amount of negative charge will appear here, because every transfer of a single charge particle increases it the same amount and decreases the other plate the same amount. Thus, there'll be some kind of electric field established in this region of space, and that electric field contains energy. And if we were to, after a time, disconnect this potential difference, the energy stays here in the capacitor, so that if at some future time we did connect a different conducting pathway between these two, we could drive those charges through that through that resistive pathway and maybe utilize the energy as the charges pass through. The idea here is, well, how much charge can we store? What is the system capable of doing? And we define that as capacitance, which is the ratio of how much charge you can drive into the circuit or drive across the circuit based on your applied potential difference. And we have found certain geometries tend to influence the amount of charge you can drive per volt. And we measure this in what we call farads and call this capacitance. So our goal is to utilize that principle to determine what the geometric consequence is. So our first and the most widely discussed kind of capacitor is one that utilizes certain symmetries and simple construction to create a capacitor. And the simple the simple geometry is what we call a parallel plate capacitor. So let's try and make it look like parallel plates. There, that looks like one. And now we'll make two. So, two parallel plates. Truthfully, parallel plates, our calculation here is going to be an estimate of the actual capacitance of a parallel plate capacitor. It's an estimate because we're going to make some assumptions about the electric field around the parallel plate capacitor. These assumptions are not true. And let's talk about the assumptions we're going to make. First, we're going to make the assumption that the parallel plate capacitor has a very large area compared with the separation distance. We're going to say that because we want to utilize the idea that an infinite sheet has a uniform electric field on either side of that sheet. So we're going to say that that's true. And by uniform, we mean that the electric field stays the same no matter where you are, no matter what distance away from the sheet you are. These are not infinite sheets. They are finite. But by saying that they have a big area compared with their distance, it's like they're infinite relative to the size and separation distance of the plates. But the truth is, although in the middle of the plates there is probably relative uniformity of the electric field, as we get to the edge of the plates, we start to get rounded electric fields that are less uniform. And we would call these edge effects. And it means that likely whatever we calculate for the capacitance of a parallel plate capacitor, the true capacitance is probably something less, which is why most capacitors come with a certain amount of tolerance that their capacitance will be within a percentage of what the assigned value is. If you're asked to do some kind of proof about a parallel plate capacitor, which happens not infrequently, what they're likely to say is that the area of the plates is much greater than the separation distance of the plates. They'll say it like that. They won't say that either one of them is approaching infinity or approaching zero. They'll just make it like that. And that's enough of a clue that you can use the uniformity of the electric field in your discussion. So in order to facilitate this discussion, I want to talk about what you do in order to use this relationship to determine the geometry of your capacitance. So we're doing this particular geometry, but here's kind of the set of steps. First, we assign the charge. We're kind of doing this in reverse, but we're going to assign an amount of charge. And we're not trying to make this hard. We're going to say that there is positive Q on one plate and negative Q on the other plate. We are assigning the amount of charge to the system. And we're going to do that at the very beginning and say that this is how much charge is on the plate. So I'm going to start at the very beginning saying this is my positive plate and this is my negative plate. I am assigning this charge to the plate. This is an intermediate variable, and I'm going to start doing that more and more because I realize a potential problem I've had with my teaching. I'm creating this variable in order to facilitate this process. But in the end, we know what we are looking for will not have charge in it. It will have nothing but the geometry of the system in it. So we're trying, in this case, to find what the capacitance will be for a parallel plate capacitor without relying on knowing how much charge there will be. Remember, the goal of knowing the capacitance is to know how well the system will store charge under certain conditions, not how much charge will be there. So we're creating this variable. It's an instance variable that will not be in our solution. So, and they won't give it to us in a problem where they ask for you to prove this either. So you assign a value of charge, Q, to both plates, positive on one, negative on the other. We're going to use that for part two. We're going to determine the electric field due to the charge. We want to determine the electric field due to the charge we've created. We created and said there is positive Q on one of the plates, so we want to use that to determine what the electric field is. This almost always is going to be Gauss's law. For the ones that we're going to do, all of them are Gauss's law. I can't think of an example where you wouldn't use Gauss's law here. And that's because of what we're going to do next. So let's start by using Gauss's law here to come up with an expression for the electric field between the plates. And that involves picking a Gaussian surface that can be represented here that will tell us the electric field between the two charged plates. Now, it's going to be hard to draw this in the way I have it here, but I want to use this image, at least for a moment, to talk about the different kinds of shapes you could possibly use. First, the shape you have to use needs to have a surface that is between the plates because you want an electric field for the portion that's between the plates. And this is where most students begin to get this wrong. And once you've drawn a Gaussian surface that is wrong, I think your graders are going to be on the lookout for other simple mistakes you're going to make. So when you're drawing your Gaussian surface, there must be a surface that is between the plates, or you're never going to score any points. Now, I have a couple of choices about the rest of that surface that I could use. Like, I think the best one is one I can't really draw here, and I'll show you what I think the best one is. But I could draw a Gaussian surface as a cylinder that has one portion, or one, like the top of the cylinder on outside the plate, and then go through the plate and have another surface between the plates. It doesn't have to be a cylinder either. A cube would do. I'm choosing a cylinder for what I think are easier reasons. A cylinder only has 3 sides. And because of that, and because of the uniformity here, knowing that it only has 3 sides means my Gauss's law function is only going to have to deal with 3 different sections. If you used a cube, you'd have to deal with every one of those surfaces instead. But if you remember doing this, you know that many of these surfaces have no flux, and so they're just going to be discarded anyways. But I'm choosing this kind of cylindrical surface. But to talk to you about some of the options you have here that I'm not able to easily show in that diagram. So let's do a cutaway view so we can talk about some other options that we could use instead that might be easier. And part of this will depend upon whether you're allowed to choose your own Gaussian surface or not. The test writers can choose the surface for you, and then you're forced to use the surface they've chosen. One surface I think about doing, and this is still the two options I think you have. So here's the cylinder as drawn in the prior one, in the prior example. I'm saying it's a cylinder. I know I don't have circular top and bottom, but I'm looking this edge on. The other surface that you could use, and this is the one if you get to choose, then use this surface, it's better. But I think these are our two surfaces. So either one where the top of your cylinder is embedded inside the plate, or one where the top surface is outside the plate and you've made it so that it's centered on the plate. So I made those choices purposefully. You should do the same. Now, can somebody in class tell me why this one is better? Tyler?
You don't have to deal with the flux through the top surface.
I don't have to deal with the flux through the top surface. That's right. Although I don't believe there is any flux through the top surface, I don't have to make any reasonable argument about the flux through the top surface. So the bottom one, because it's inside a conductor, has to have no electric field there, and that way I don't have to worry about the flux there. So if you're using this surface, you might have to make an argument as to why the electric field is zero or nearly zero here. You don't have to do that here because it's inside the conductor. Can anybody make the argument as to why the electric field is zero or nearly zero here? None of you can? You're smart students, supposedly. Shockingly condescending. Yeah?
The charges from the top and bottom plate cancel out, and no charge goes through the conductor to the top.
So, mostly right. If this is the negative plate and this is the positive plate, and let's color code this so that we have at least kind of a way of looking at it. So negative plate. The negative plate has electric field lines that go this way, right? That's the electric field generated by the negative plate. But the positive plate will have, field lines that go this way and this way, right, across the top of that plate. The green line here is downwards. Effectively, the top plate and bottom plate create electric fields that are in opposite directions, and since it's a uniform electric field based on the same amount of charge, the electric field out here should effectively be zero. Now, for a real parallel plate capacitor, that's not true. Because for a real parallel plate capacitor, this distance isn't infinitely small compared to the area of the plates. We won't have perfect electric field cancellation outside, and you probably will have some residual electric field outside the plates. Remember, we are dealing with an ideal circumstance, and this is saying that we're dealing with the ideal circumstance, but making it look like, it's not really ideal because the parallel plates are far apart compared to their area. That's why we try to get the plates as close as possible so that we can make them more ideal. But either way, that's the argument you have to make for why the electric field is zero outside the plates. All right, Owen. Again, you guys should be more seasoned than you were back when we did this back in October. So my expectation is that by telling you different choices that you have, don't be thrown off. The most common mistake students make is to make their Gaussian surface look like this, which is clearly wrong and not going to tell you anything. Or worse, they do something silly like this. Well, now I have no surface between the plates. How do I know what the electric field is between the plates? This is what you have to be careful about when you're dealing with your Gaussian surface. So I'm going to choose this Gaussian surface here for this work and not this one. Is that okay with you guys? All right. So I don't need any of this stuff anymore, so let's get rid of it. And I don't need this guy anymore, so we'll get rid of it. And I'm going to go ahead and do what we have to do now. There's the top surface, the bottom surface, and the sides. I know that there's an electric field this way. I think the electric field is uniform. I think the electric field is all in the same direction. And I know from using Gauss's law before that the electric field next to an infinitely large sheet of charge is sigma over 2 epsilon naught. I do not have to reprove that here. Okay? You could. We have Gauss's law. But I think the electric field is going to look like this. I'm reminding myself. Okay? Now, you don't necessarily need to use this. In fact, we're probably not going to. But you should remind yourself that that's what it is and that it's uniform. That way, it's something that you've memorized that you can kind of check against what you're actually going to have here. Because we're not going to have sigma in our answer. But we should get something that looks like this for our answer. Not exactly this, but like this. So I start by saying that the flux is going to be equal to E dot dA. Modern exam doesn't spend a lot of time on this. It's just expecting you to take this, separate it into your 3 portions, and you might not even get credit for doing all of this. You don't really know what they're going to feature or what they're looking at you doing. Some years, none of this actually adds any points. You just have to decide. Based on what I've written here, there's no flux through the side because of the dot product, right? The electric field and the direction of the area are 90 degrees to each other, so the cosine is 0, right? You guys understand that portion? The direction of the area is this way, and the direction of the electric field is downward, so I get no electric field going through that area. The dot product produces a 0. You need to be able to explain it in case they ask. Also, there's no electric field going through the top. It's inside a conductor. Electric field everywhere in a conductor is 0. Automatically makes that particular portion 0, which means that my electric flux is just going to be E times the area of the top. Whatever that area is, and I don't know what that is. I don't have to. I do have to do the next part, though, because we need an expression for the electric field. And this has to be used in the service of Gauss's law. And in Gauss's law, Q enclosed equals epsilon naught times the flux. Here, you do have to be a little more careful. The Q enclosed is going to be related to what the area of the top is. That you do have to be careful about. So although we have an area here, that's not the area of the plate. That's the area of your Gaussian surface. You need to find a way of writing the Q enclosed in terms of the area of the top. When you're trying to find capacitance, and again, this was 2 days ago, 3 days ago, it might have been on my birthday. Anyways, what I was trying to say before I was so rudely interrupted. 2 pieces of metal. Step 1, apply equal and opposite charges to both pieces of metal as if they had been driven that way. Step 2, use some method. Any method will do, but it's probably going to be Gauss's law, to come up with an expression for that electric field in terms of the charge you applied. We're doing it this way on purpose because we want that charge to physically cancel out in our expression for capacitance. Step 3, now that we have derived a function for the electric field, you need to calculate the electric potential from the low potential side of your system to the high potential side of your system. When all 3 of those steps are complete, you can sub in the expression for the electric potential in the equation for capacitance. So again, I'm just trying to start back a little bit from the beginning because I remember the day I was doing this, I was not particularly articulate, and I'd rather be articulate. So that's what we're doing. So our step 1 was to say we have charged the plates. There is a charge of Q on the top plate and negative Q on the bottom plate. And that's where we started. Next, we need to figure out the electric field that is created between the plates due to the charge we placed on these plates. And I'm using the word plates here, but remember that word is generic. It means any two pieces of metal. We're saying plates because it's a parallel plate capacitor. But I want to be very clear, just the two pieces of metal. We need to find the electric field due to that charge. You're likely going to use Gauss's law. It's the right choice to make, unless, for whatever reason, and there's no reason they couldn't do this on the exam if they really wanted to hurt you, by having some kind of weird shaped set of pieces of metal and have you find the capacitance by having you use, say, Coulomb's law and the assembly of charges to determine what the electric potential is. Now, there's certain reasons they can't make it too crazy, and that is if they gave you like an odd-shaped piece of metal, the electrons wouldn't necessarily line up in a uniform way on that piece of metal. And so they're unlikely to do that. But they are likely to do this, which is why you're going to use Gauss's law to come up with an expression for the electric field, because there's probably going to be some kind of exploitable symmetry. Again, this is something that's real. And I say this because, parallel plate capacitors are something you can build yourself. We built them last year when we were making the aluminum foil with the book thing. Do you remember that? So it's very likely you do it this way. But the AP exam has made it pretty clear that they can dive off into other things and have you do other things with that information. So we're in the middle of finding the electric field. We were doing so by using Gauss's law. We're using a shape that was kind of cylindrical, and we put one of the surfaces of that cylinder inside the top plate, so we knew the electric field would be 0. We made the cylinder perpendicular to the plate, so the electric field had no flux through the sides, which leaves only one portion of the plate necessary for us to, one portion of our surface necessary for the Gauss's law part of the formula, and that is, this part right here. That's the only place where we have any electric flux. There are electric field lines passing through the bottom of that cylinder, and we're saying that the A here stands for the area of the bottom of the cylinder, not the area of the plate. So I'm saying this because we probably need to start differentiating the area of the cylinder, and the area of the plate. They are different, and we were probably going to need to use that. So let's consider maybe not using capital A here and use something that might be, at least different enough. So maybe I'll say that it is a true cylinder, and pi r squared is the area of the bottom of that cylinder, just so I have something separate completely. You guys understand what I'm doing? That way it doesn't get in the way of the area, because in a few seconds we're going to have to figure out the charge enclosed. And to get the charge enclosed, we are likely going to have to deal with the charge density. So let's kind of slide this to the side a little bit. And I want to do two things real quick, because this is supposed to be review. And in that, I don't always want to be reviewing just one thing at a time. So imagine we expand the piece of metal, and we're looking just at the part where I have my Gaussian surface in there, but I'm trying to get like a zoomed in part. So my Gaussian surface looks something like this. I want to remind you, if we are depositing charges on the plate, and we say that the top plate is positively charged, and that occurred because we removed electrons from this plate and pushed them to the bottom, it should be noted that the positive charges will be on the inside surface of this plate. So even though we buried our Gaussian surface, so that it was inside the metal, the charges exist on the surface. So this will still be the charge enclosed. Everybody understand that? I'm trying to make that very clear, because when we did this first semester, we had our Gaussian surface on the outside, but indicated and made some argument about how the electric field is 0 out here. But there's been several AP exams where they have forced the Gaussian surface to be used in the way they've drawn it, and they draw it with the Gaussian surface inside the metal. This is why we're able to do this, because the charges are going to exist on the surface of that metal. So, throwing that away for a bit, let's take a look at, this is the plate, and we're looking top down on the plate. And our Gaussian surface is a cylinder. So this is the top of the cylinder as it looks embedded in the plate. Everybody okay with that drawing? Everybody good with it? This is the way we go yes, and this is the way we go no. And if you're not sure of it, just sit there stoically, maybe sleeping. Okay, so we're all stoically. So we're good? I can go forward? Excellent. The whole plate has charge Q and has area A. So the surface density of the charge is Q over A. We need Q enclosed. That's what we're going to be trying to shoot for here. So Q enclosed is going to have to be the charge density times the area enclosed. And I'm just trying to pick up the little pieces here that we tend to forget. So the area enclosed is going to be the area of my Gaussian surface here, because that's the part that's enclosing a portion of the charge. Yes?
When you're doing Gaussian law, how do you know when you have to use charge density?
You always have to use charge density, but they don't always give you the charge density. They might give you some information you can be using to find the charge density. But technically, your charge enclosed is always going to be the charge density times a length, an area, or a volume enclosed. Because your Gaussian surface is enclosing some amount of charge. So in this case, they didn't give us sigma. Sigma is a placeholder for us to be able to drop in Q over A, something they probably did give us, the area of the plates and the charge on the plates. So it's unlikely for them to have just sigma there, or unlikely to have lambda. But we have seen situations in which they've given us lambda, or our expression might end up with lambda in it for the electric field. We've had that happen before. Is that okay?
So like when we do,
So like?
when we have little r squared over big R squared, is that just basically charge density except we got rid of like the pi's? If it's like a spherical?
So yeah, I mean, because I think I see where you're going with this, but it would depend on what our geometry was and how we structure. Like, what if they didn't give me A, but they said that this was side length L and this was side length W? Then I'd have A over L times W, right? And L times W would probably be in my answer somewhere. So I can't speak to every situation, but you're probably going to be using area of a circle, volume of a sphere, volume of a cylinder. You know, you're going to be using some basic shapes and some basic geometry, and usually getting your Gaussian surface, Gaussian volume, and all that stuff.
Thank you.
Oh, you're most certainly welcome, Vicky. That was not condescending. That was perfectly nice, wasn't it? I'm not even being shockingly condescending. That was very nice. I mean, I dealt with the so problem at the very beginning. We're done with that, right? We're good. No ums.
Well, it's not like Owen. Owen goes,
Oh, let's not throw Owen under the bus anymore. Let's be nice to Owen until later when he says something. Oh, man. Sergio's next. Sorry, guys. And so I understand your question now. And now that I hear your question, I can answer it with a little less shocking condescension. In this example that I drew here, even when I had it, drawn so it was like this, you're wondering why we're not dealing with the volume in here. Is that a fair assessment? And there's two reasons why. First, this is not an insulator in which the entire material is a slab that has a uniform charge density. That's not what this is. This is a piece of metal. And on any metallic surface, your unbalanced charges will reside on that surface, either spread out uniformly, or if your surface is of a weird shape, then maybe concentrated in other areas in order to ensure the electric field inside that conductor is zero. So we're good treating the area of this as just a simple area, since its charges aren't spread out throughout the volume. They are just on the surface of that plate.
So do we have to explain that, or can we just
No.
write sigma?
No, this is accepted practice. And so you're fine. You don't need this explanation. And you shouldn't be asked, I mean, you could be asked this to explain it, but you shouldn't be. An insulator, the charges can be spread out throughout. On a conductor, they're not. On a conductor, any unbalanced charge will be on its surface. It's the definition of a conductor. In the same way that you don't have to explain that the electric field inside a conductor is zero, you're allowed to just know that and state it. It doesn't require an explanation. You can start from a point that the electric field inside any conductor is zero. That good? Yeah. All righty. And eventually, we're still trying to get to middle of step 2 here, using Gauss's law to find an expression for the electric field. Let me just remind us where we are, because it's been 12 minutes since we started. I got a little running counter here. Q enclosed is going to equal Q over A times pi r squared. And this has to match the area we used a minute ago, right? The area for our Gaussian surface is going to match that. That's our goal here. That's why we're doing it this way. That's why we're playing with the symmetry. So once we've done that, we're going to bring these things, whoops, not really there. We're going to bring these things together to Gauss's law. We're coming up with an expression for the electric field in terms of our, in this case, our charges on our plates and now I'm stumbling. Let's just get to work. So for all of you people who remember how to do this, this is just algebra now. So do the algebra. All right, just algebra now. We would expect the electric field inside between the plates to be constant, because we know that the electric field from a large sheet of charge is uniform. So the pi r squareds cancel out, and I get E equals Q over epsilon naught times A. There are things here you should recognize. And if you don't, it's about time you started. First, if we have a single charged sheet in space, the electric field is sigma over 2 epsilon naught. This electric field is twice as strong as that because there are 2 plates. And although we never used the contribution of the second plate, you'll notice it works out anyways. And that's because of the way in which we use Gauss's law. Had we done just a single plate, you'll remember, a single plate, metal or not, our Gaussian surface would be on both sides because there would be an electric field on both sides of the plate. Right? So we would have had a flux, bless you, through both surfaces here. Right? Because we had 2 plates and they're of opposite charge, the electric field on one side of this was 0. And we get a concentration of that electric field between the plates. But you should remember that this is the contribution to the electric field near any plate of uniform charge or any sheet of uniform charge. The fact that we have 2 of them doubles it. So if you were not asking to derive, you could start there if it's just determine or show. But derive has a higher threshold, especially if they say derive using Gauss's law, the electric field between the plates of a capacitor. All right, so that essentially finishes step 2. Takes a long time, but there we go. All we needed was an expression for the electric field, which is what we have. Step 3, you now have to find an expression for the electric potential. And it doesn't really matter if you go from the low potential to the high potential. You need the absolute value of the electric potential. So whether it's positive or negative will make no difference. So especially on the AP exam, where you don't have a whole bunch of time to spend thinking about what you should do, jump to the relationship and work on the electric potential. So step 3, we're going to grab the electric potential function, and we're going to try and come up with an expression for the electric potential from one plate to the next. Yeah, I am going to go from the bottom plate to the top plate, and I'm going to state this as 0, and this is a distance d away. And I'm going to note that this is this is the dot product. So that should be the cosine of the angle between ds and the direction of the electric field. And it's going to be 180. And it's going to cancel out those negative signs because I should show an increase in potential from the bottom plate to the top plate. But all I really need is the absolute value of that electric potential. But I'm still going to dump all of that in there because I spent all that time saying it. And since I like to word vomit a lot, I think I'll just go ahead and put all the vomit on the plate. So E is going to be Q over epsilon naught A dot ds dot cosine of 180 degrees. Technically, that's all the things that you should do. So most all that's a constant. The cosine cancels the negative sign. And this just leaves us with QD over epsilon naught A, the electric potential going from the bottom plate to the top plate. Step 1, place charges on the metal. Step 2, find the electric field due to those charges. Step 3, find the electric potential due to that electric field. Those are the 3 steps. I didn't do all the integral stuff. Does anybody need me to go into any more depth here? All right. So this was the end of step 2. Step 1 was just putting the charges there. So now that we have done all of those things, we can determine the capacitance in terms of our geometry. So just a reminder, I'm just going to leave all that kind of exposed. The definition of capacitance is how much charge do you get for your applied voltage. We worked it backwards. We said how much voltage do you get for your charge, but it's still going to give us an expression for the capacitance. So we leave Q here, and we pop in our expression for V, which is QD over epsilon naught A. Cancel the Q's. If you've done this right, the actual charge needs to cancel. You need a final expression that isn't about how much charge is there or about the potential. What you need is something that is purely about the geometry of the system. There it is. That's all there is to it. So, we have limited time. You try it for a cylindrical capacitor. See if you can write out the steps. See if you can do the pieces. So, and I'm not trying to make it hard. Let's make it relatively, straightforward. I have a cylindrical capacitor that has an inner radius R1 and an outer radius R2. And as you saw first semester, it's hard for Mr. Shelton to draw anything that resembles something nice. So this is good enough for us. Do you need me to draw like some 3D badly exposed version of this? Good. So let's state that ultimately from the side, perhaps this looks like, I don't know, something terrible. Something like that with an inner radius and an outer radius. And I'd like to indicate that this distance, and D is not part of your answer. I'm just saying that this distance is much less than how long the capacitor is. All right, this is to ward off the edge effects. All right, so your job has 4 distinct steps. Step 1, apply charge to your 2 conductors. Step 2, determine the electric field created due to the charge. Let's go ahead and indicate that this is L long. All right, so I'll give you a minute to do that part. Your step 2 is likely going to be a derive, where you'll have to derive the expression for the electric field using Gauss's law. So attempt that, try it, please.